All right, let's get started. Hi everybody. Welcome to the penultimate SNAP of the semester. Today it's our pleasure to have Daniela Hurtado-Lange joining us. Daniela is an assistant professor at the Kellogg School of Management at Northwestern University. She received her PhD from Georgia Tech, for which she won the Sigma Chi Best PhD Thesis Award. Um, she also spent time as a research scientist at Amazon, and some time as a assistant professor at William and Mary. And so today, Danielle is going to tell us about the transform method for Markov-modulated cubes. So please take it away, Daniela.
Thank you, Zip, for the introduction, for the invitation. I'm super happy to be here. Um, and thanks to the audience for being here on the Monday right after Thanksgiving. I know it's probably one of the most difficult Mondays ever. Um, so as I go along, please feel free to ask questions. I'm not very good at monitoring uh, hand braces or anything, so just uh, I'm
I'll be
okay
watching the
with
chat.
myself. What?
I'll be watching the chat, so don't.
Okay, cool. Yeah, just let me know. And yeah, let's make it interactive because I only see names and I'd love to know there's more people on the other end too. All right. Today I'll be talking about a project that Izzy and I have been working on for the last maybe year and a half or so. Um, we're still writing the paper, but it'll be out soon, and you'll find it available on my website as soon as we finish it. So the key motivation here is that waiting in line is annoying, right? We've all faced long lines. And the line on the left right now, it's an old-fashioned line in some sense, because people are waiting and we can see. But many times we also face lines where we know we're waiting, but we actually don't know much about how long we're waiting, and it becomes even more annoying. When I say annoying, I also mean there's dollars behind, right? We know that when people wait in line, their experience gets worse, and that costs money. There are several examples of how we can quantify how much money that costs. In particular, if this is not people and their jobs in a data center, so on and so forth. There's amazing numbers showing how 1 second delay can cost millions and millions. But today I want to bring a very concrete example. And me being not American from origin, this is very American to me. You can actually pay someone to wait in line for you. And here is an example. I took it from TaskRabbit, where you can just, get a request and someone will wait in line for you. But there is many ways to get this done. Indeed, some of my colleagues, Marty Lariviere and Achal Basambu, are working on a paper where they study the economics behind paying someone to wait in line, so line sitters. So yeah, all that intro to say that my ultimate goal, and I guess the ultimate goal of a few people in the audience today, is to minimize delay in a variety of settings where we wait. And of course, delay is a very complicated object. So today we're going to be focusing on one step before minimizing, and we're going to be looking at how we understand delay. So let's start with the simplest possible system, a single server queue. This arrow indicates there is jobs arriving. The circle indicates there is a server, and then after being served, they leave. When the server is busy with a customer here, the others wait in line. Um, and I mean, we're not going to be talking about this, how we schedule what's the next one to serve, etc. But just to say, this is the simplest system and it's well understood, meaning that the distribution of the queue length in steady state is known. And indeed, there's many attempts to predict the queue length, the PMF of the queue length in transient. So now, if we want to move a little bit more complicated, we can put a bunch of single server queues in parallel. And here, this yellow waves is my best attempt to draw correlation. So correlation, it can be just as a definition that we all learned in our first probability class, just two random variables that are tied together, but it can be more concrete. So for example, there could be a control here that tells me where a new arrival goes, or similarly a control on the other end that tells me which jobs I'm going to process. Another way of drawing multiple queues is a network, right? Where there's a bunch of single or multiple server queues, and then after leaving one queue, you go to another one, and then you may leave the system, or you might join another one if you go down this path, etc. And in these cases, we still would love to understand the distribution now of the vector of queue lengths. However, that's hard, so we start simplifying the question. Can we understand the mean of the vector of queue lengths, the variance or covariance? And that's also hard. So sometimes can we simplify further and look at the sum of queue lengths in terms of distribution, mean, variance, or the tail probabilities, right? Because we would love to tell our customers the probability that you wait more than 5 minutes is, less than 1% or so. So for networks of queues, we typically model them as Jackson networks, and in that case, if all the times are exponential, the distribution is product form, and that's also well understood. Today, we're going to focus on multiple queues in parallel, and single hops, so meaning that there's one arrival, then once you're served, you leave. Now, of course, I'm not the first one, or we are not the first ones to look at this type of system. Um, and the typical approach is to go for an asymptotic regime because understanding them exactly is very, very hard or intractable. So just a reminder of what asymptotic regimes are, maybe one of the classics is large deviations or rare events where we look at the tail probabilities and we take the value here to infinity. So we look at the probability of waiting a lot, right? And we want to minimize that. Um, Another asymptotic regime is mean field, where we look at what happens when the number of servers grows to infinity. And then there's a bunch of techniques to analyze this. The one I have more experience with is heavy traffic, where the number of servers is fixed, but we take the limit as the arrival rate grows to the service rate, right? So uh, we're loading the system to the maximum capacity. And there's something in between these two that has had a lot of attention in recent years. It's called many server heavy traffic, where we take both the number of servers and the number of servers to infinity and the arrival rate to service rate. And depending on the relationship between these two limits, right? We have different regimes such as halving weight, non-degenerate, slowdown, or in between. So as you can see, each one of these asymptotic regimes has a long line of literature here. Of course, I'm not listing everything. That's why I have dots everywhere. But all this literature focuses on systems where the arrival rate and the service rates are constant. And this is a big assumption in many scenarios. So let me tell you a few examples of where this may not be true. I guess arrival rates are the most intuitive. We have good understanding that there's peak hours, or that customers come in batches, or if you're in the US, I don't know where else we have Krispy Kreme. Even the servers or the controller can generate an increase in arrival rates, right? So when we see this sign by a Krispy Kreme store, we know that the donuts are hot, and then you have to be very careful if you're driving by one, because many people try to go in the drive-through and get their hot donuts. For service rate, I would say it's a little less intuitive how we could have a variable service rate in time. And here's an example. So this is the checkout area of a supermarket. That's the cashier, and this person is bagging. But I mean, even when we see two people, they are actually acting as a single server, right? Because they are working on the same order at the same time. And if the bagger needs to do something else, say open another cashier, another checkout, or go replenish something, or go to customer service, etc., this person still processes, but at a lower rate. So, for example, we could model the service rate varying with time as the moves of this guy. Or in computer systems, there's a concept called working vacations, or in manufacturing they use it too. And it means basically the server slows down a little for a while, and then it goes back to its original speed. So, for example, in my example of the checkout, a working vacation could be when the bagger is not here, and then they go back to their original speed when they are both together. So let me look at the literature with varying arrival rates. Here we're going to focus on Markov-modulated parameters. The advantage is that Markov-modulated arrival processes are dense in point processes. So basically we're capturing a lot of the potential variability in the arrival and service rates. So the literature is also very extensive. Here I have a few examples. Most of the literature on Markov-modulated queues concentrates in the 80s, 90s, and early 2000s. And in that couple of decades, people were studying mostly a single queue with finite state Markov modulation. Many times a single server queue, a few times a single queue with multiple servers or even MM infinity type of queues, um, which, I mean, we agreed already that we're going to look at multiple queues. There is another attempt at a multiple queue with multiple servers in last year, where they studied an input queue switch with Markov-modulated arrivals, and they computed the distribution when state space collapses to a single dimension. I'm going to explain what that means in a minute. However, in an input queue switch, the service rate is not only the service rate is constant, the service time is constant. So every job takes exactly one time unit to be processed. So in this talk, I'm gonna focus at the intersection of both. We're gonna look at Markov-modulated queues in heavy traffic. So we're gonna look at a system with multiple queues and multiple servers. Our arrival and service rates are going to be Markov-modulated, countable state space, so beyond finite state. And as I said, we're gonna look at the heavy traffic limit. Okay. So, with all that introduction, let me present you with the model. We're gonna use some sort of canonical model that includes many of the complexities we see in other systems. We're gonna look at what I call the JSQ model. It's also called load balancing or supermarket checkout, and it's as follows. So there is a single stream of arrivals, and we're gonna model the arrivals as a Poisson process with rate lambda I. Upon arrival, a single router will send this arrival to the shortest queue. If there are ties, we're gonna solve that at random. And then each of the servers operates independently, meaning not independently in the probability sense, independently as in each one has their own queue and does their own work. And they have a different service rate. Each server has a service rate mu ij. Now the orange and the I are because these rates are Markov modulated, meaning that there is a Markov chain running in parallel. And the state I of this Markov chain will tell me what's the arrival and what's the vector of arrival rate and what's the vector of service rates. And we're going to use raw pi as the expected load, so expected arrival rate under the stationary distribution of this Markov chain divided by the expected total service rate. And I'm going to use epsilon as 1 minus rho. So as epsilon decreases to 0, we're approaching the heavy traffic region. Now, regarding assumptions on this Markov chain, I would say pretty mild assumptions. We want a countable state space. We want the stationary distribution to exist. And we want arrivals and service rates to be bounded. Okay, so no explosions. And the result is what uh, we would expect in heavy traffic. So we take the vector of Q lengths, we parameterize, we multiply it or scale it by the heavy traffic parameter epsilon, 1 minus rho, and then we show that it converges in distribution to a vector of exponential random variables with a certain mean that depends on the variance of arrival and service times in steady state. Now, notice there's a condition here. I said for lambda I large enough for each I, and I'm gonna get to that once we go through the key steps in the proof. Okay, so as I said, this result is not surprising. Is what one would expect, and our key contribution is how to obtain this result when the arrival and service rates are Markov modulated. So let's go through that. Um, So that's the result for reminders. And we want to, so in the proof, we start with the epsilon times the vector of Q lengths, and we want to study that object. We're going to do that in two steps. The first step is state space collapse, where we show that the vector of Q lengths here actually can be approximated by a single server queue, or in other words, is sufficient to understand the behavior of the sum of Q lengths. Um, and then in the second step, we study the heavy traffic distribution of the sum of queue lengths scaled by the heavy traffic parameter. And in the second step, we will use a transfer method and Poisson equations, both concepts I'm going to define in a minute. Okay. So any questions so far? All right, so let's move into the proof. First, state space collapse. So as a reminder, we have this multidimensional system n queues, and we're going to show that as the load increases, as epsilon decreases to zero, we can approximate that by a single queue that where the queue length is the total queue length and the arrival and service rates are the total arrival and service rates.
All right.
So yes.
And Daniela, actually, I have a question. What does it mean for epsilon to go to zero? Does it mean are all the lambdas scaling uniformly, for example?
So the um yes, the lambdas are growing, or they could even be concentrating across to a lambda pi. Um, so in terms of how the limit is taken, there's the transition rates here are kept constant, and the values lambda and mu's are so that they converge to uh, you know the same value.
Mhm. Okay.
Does that make sense?
So I guess if the rates are being kept constant in the transitions, then I think this is the thing I'm confused. Oh, is it that each state has its own lambda I and mu?
Yes, each state
Oh,
has a
okay.
lambda I.
Okay.
The rates of the arrows here are kept constant, but the values in the orange circles can move.
Got it. Thanks.
You're welcome. Um, all right, that's a great question, actually. So, all right, so we have our state space collapse result. Formally, this is the result. We're going to define an object called Q parallel, and this Q parallel is a vector where is the vector resulting of projecting the actual vector of Q lengths on the vector of ones. So Q parallel is a constant. I mean, all the values in Q parallel are equal. And then Q perpendicular is the difference between Q and Q parallel. So in some sense, Q perp is measuring the error of approximating this system by this other system. And then the result says if lambda is large enough for each state I, then the norm of the moments of the norm of Q perpendicular are bounded. So, and I see how this could be a little bit of a disconnection. I said I'm showing that this system converges to that one, and now I'm just telling you the error is bounded, but I'm not telling you anything about the constant. The constant could be huge, right? But remember, we're in heavy traffic, so let's see how this works. In two dimensions, this is Q1 and Q2, and that line is where Q1 equals Q2. Let's say the vector of Q length is this brown vector. Then q parallel is the projection on this line, right? So that vector over there, and then q perpendicular is that vector there. Now, if we decrease epsilon, so we increase the load, then q, the vector of q length should be longer, right? So will be the projection. However, the error vector q perpendicular stays around the same, right? And then since we are multiplying everything by epsilon, this becomes negligible, and we can approximate the vector of q length q by the projection q parallel. The proof is classic drift analysis, so I'm not gonna go there. Um, and I'm gonna focus on the proof of the second part where we analyze oh where we analyze the distribution of this one. Now let's dive deeper into this condition lambda I is large enough. So remember, this happens in heavy traffic, right? So if these rates were constant, then lambda and total mu should be uh, close enough so that we have a balance. If I have one arrival every, I don't know, 100 years, then the QNX will never be equal, because whenever I have an arrival, I break the balance and I don't have so many arrivals to make all the Qs equal again. So lambda I large enough is this condition. And let's look at it a little bit closer. First, observe that if all the servers are homogeneous, meaning that the service rates are equal, the right-hand side is zero, so we don't need anything. And so in some sense, enough arrivals depends on how heterogeneous my servers are, right? How big is the total service rate compared to the smallest possible service rate I could have. Um, so the arrivals need to cover the range of service rates, and the intuition is exactly what I'm saying. So I can only balance my queues when arrivals happen. So I need enough arrivals happening regardless of which state I am on. And then I'm gonna have JSQ balance my queue lengths. So in some sense, this condition says when can JSQ balance the queue lengths? And an observation here is that we're not assuming anything about the mixing time of the modulating Markov chain. One could say, well, why do you want all of them to satisfy this condition? On average, they should be large enough, right? I can have a very bad state, and that's okay. And the answer is yes, but in that case, you need conditions on the mixing time. So it's one or the other. Um, So that's with state space collapse. In order for this to be satisfied, we need lambda large enough. And then in the second part, we're going to look at the asymptotic distribution of the collapse system. So I'm not the first one doing heavy traffic in life, of course. For a long time, the most popular approach for heavy traffic analysis was the diffusion limits approach, where, as similarly to now, we want to study the scaled vector of Q lengths, or single Q lengths. And we want to understand its behavior in steady state. However, this limit is hard to take. So people started taking the heavy traffic limit first and proving convergence of this scale Q length to a reflected Brownian motion, and then studying the steady state of this reflected Brownian motion. Now, I assume we all took multivariable calculus at some point, and we understand that the limit in brown may not be the same as the limit in green. So a key step is showing that those limits indeed yield the same object. And this interchange of limits step is typically super hard. Indeed, in many, many cases, there's one paper studying the Brown limit and another completely new paper studying the interchange of limits proof. So that was the most popular for a couple of decades. More recently, in the last maybe 10 years, there's been a new focus on what actually Jim Dye calls direct methods. And what it means is that we directly study the limit in green. And so the limit in green and then in purple. So one method is times method, where one looks at the Wasserstein distance between what we want to study and what we know how to study. Um, there's also the drift method where one computes the moments of the scale Q length and then inductively computes the distribution. VAR approach, where one studies e to the power epsilon q and one bounds the jumps appropriately to understand the distribution. And there's transform methods which is kind of some sort it lands a little bit in between the drift method and the VAR approach because we study the drift of an exponential function and compute the moment generating function. Um, I'm gonna focus on the last one because I like studying distributions by looking at expectations because expectations seem easier in my world. Of course, we're gonna hit some roadblocks, and I'm gonna show you how to deal with that. Okay. So let me show you first the transfer method for the simplest Q and MM1Q. So that's a picture. We have a single server, an open queue. Arrivals occur according to a Poisson process at rate lambda. Service rates are exponentially distributed with rate mu, and the load is lambda over mu. So we're going to look at the drift of the following exponential test function, e to the power theta q. And when I say drift, I mean what's the expected change in this function in small amounts of time. So what can happen? There could be an arrival or a departure, right? If there is an arrival, then my quantity q becomes q plus 1. And if that happens at rate lambda. And if there's a departure, my number q becomes q minus 1. That happens at rate mu. And it can only happen if there's someone in line, right? If the queue is empty, there cannot be a departure. So that's what this indicator is doing. We reorganize terms in a more convenient way. So we put all the e to the power theta q up front. And then we evaluate, and then this indicator of q positive, I'm going to write it as 1 minus the indicator of an empty q. So it shows up here. Now, the next step, we want to take the expectation of this drift because it should be 0. So we get a 0 on the left-hand side, and then we deal with the right-hand side. And to do that, we need to make sure that there's only one random variable multiplying each other, right? The expectation is linear, so we want to make use of that property. In the first term, we have e to the power theta q here. This is a parameter. These are parameters because it's the MM1Q, is not Markov modulated. Good. The second one, parameters. And then this is a little problematic, right? Because I don't know how to deal with the product of two dependent random variables. However, if we look at it a little bit closer, it's not too bad because when the queue is empty, then so the indicator is 1, then this object is 1, 2, right? E to the 0. And when the q is positive, then the indicator is 0. So whatever this number is, it gets multiplied by 0, so we kill it. In other words, we can replace this product by this term, by only the indicator of q being 0. And then with that, I mean, we solved our problem. So we can take the expectation. Expectation of an indicator is the probability. So we're not quite done yet because supposedly we don't know this. But to compute it, we can set theta to 0. And if we set theta to 0, we immediately obtain that the probability of an empty Q is 1 minus rho. Then we put this 1 minus rho over there, and we show that this is the moment generating function of the Q lengths. And if you do a little Google search, you realize that's a geometric distribution exactly as we know. Okay, so that's the transfer method. Any questions? All right, let me move on then. So let's do an immediate jump to the transform method for Markov-modulated joint the shortest queue. So as we already showed, this vector of queue lengths behaves as a super single server queue. So we're gonna do the transform method for this single server queue because we already know how to do single server queues, right? So um, I'm gonna do a exponential test function. Right now, since this is not an MM1 queue, I have to I have to use the scaling epsilon q before I could just put any theta here. So I'm gonna do s epsilon q sum, y q sum, because that's my single server queue. And then I'm gonna look at the drift. So similarly to before, there could be an arrival or a departure, and the departure is linked to a queue being non-zero. So I skipped the first couple of steps and I directly wrote the rearranged terms. And orange indicates Markov-modulated. So now, as in the MM1 queue, we want to take expectation. So if we look at the first term, we have a parameter, we have a queue here, and then these guys are Markov modulated. So actually, I cannot, this is, if I take the expectation of this term, it's not the product of the expectations because the arrival and service rates influence the queue lengths. So, okay, a little bit of trouble there. Let's see if there's more hope on the other term. Parameters, e to the q. Oh, orange parameters, multiplying them, and an indicator. Okay, so this looks quite complicated. However, I do remember from my MM1Q that there was a trick to get rid of the dependence e to the power q and indicator. So let's see if we can do that here. So remember that this total queue length um, means the fact that we're analyzing this total queue length means that all the queues are kind of similar, right? So if the total queue length is positive, it means probably all the queues should be non-zero. And if this is zero, then it means, of course, that all the queues are zero. So let's try that would be what state space collapse tells me, right? So let's try to formalize that. So state space collapse tells me all the queues are approximately equal. So the sum of queue lengths can be actually approximated by n times the individual queue length. And then we're very familiar with this object, right? The product of these two is just the indicator. So I get rid of that term. And I pay a small price, which will become an order epsilon squared term. Okay, so that's easy. And then are we ready to take the expectation? Well, not yet, right? Because we still have this product and we have this product. Now, in the single server queue, we also had a mu times indicator. And what we did was setting S to zero and then dealing with the expectation of that. We can do the same here and we can easily compute the expectation of this term. So that's easy. The only complication left is this product over here. Okay, and the problem, of course, is that queue lengths and arrivals and service rates are not independent. So I really don't know how to compute the expectation of this product. And when you're stuck in something like this, you work with Izzy, who's an expert in Poisson equation. So that's what how we're gonna deal with it. Okay, we're gonna use a Poisson equation to separate this expectation. So let me tell you what's a Poisson equation. So for any continuous time Markov chain with countable state space Z, such as here, we're gonna use alpha to denote the transition rates. And then we're going to consider a function f, which has a finite expectation f bar. Then Poisson equation says there exists a function vf from the state space to real numbers that satisfies this equation. Let me rewrite it in a more amenable way. So if I rewrite this on the right-hand side, I get kind of the deviations from the mean of each state I in terms of the function f. And then on the left-hand side, I have the drift of the solution. So in some sense, this Poisson equation is measuring how much each state deviates from the mean in function f. Okay, so let's keep this one in mind. Now, how do we use that in our context? Well, using the solution to the Poisson equation, we prove the following key theorem. And I know there's a long, long line here, so let's go step by step. First, we're going to be able to characterize the covariance between e to the power s epsilon q and a function f of I. What's the covariance? So the covariance is the expectation of the product minus the product of the expectations. In our equation before, we had expectation of products, and we want to use the product of expectations because that's easy, right? So first we're going to be able to separate the product of expectation. And as anything in life, there's a price. So we're going to characterize the error of this approximation. And this error has some S epsilon terms. And here we have the solution to the Poisson equation plus some other bounded terms. Now, what is this eta? It's a condition on the solution to the Poisson equation. Basically, we want 1 plus eta moments to be finite. And this theorem is not difficult to prove using the Poisson equation. It's still, the difficulty was in coming up with the right thing to do. So let's see it in action. Oh, that's another term. We had this expression where we have the drift of my exponential function. And we want to take expectations. So if I take expectation at the steady state, we get the following expression. This is a 0, and then on the left-hand side, I'm going to keep this one, and I'm going to move this to the right-hand side. I also canceled this term. And we already observed that the right-hand side term is easy to compute. Now we focus on the left-hand side, and to compute this term, we're going to use the theorem. So let me refresh the equation. We want to compute this guy. So first, I want to use my e to the power q term times a function of I. And that function of I has to be strictly function of I, not of s, not of epsilon. So I'm going to expand this in Taylor series for a couple of terms so that I only have parameters depending on I on the expectations. That's the result. And then we have two terms that depend on q and I, q and I. So I'm going to use my theorem twice with function f in blue and then again with function f in green. I use my theorem and then the left-hand side becomes this huge thing. Let's look at it step by step. Here we have the moment generating function of the scale q lengths. Good. Parameters, parameters, parameters. Great. More parameters. And then here I have my moment generating function. Oops, solution to the Poisson equation and then more parameters. And this is of order epsilon. This is also of order epsilon. So I need to actually compute this guy. And then some error term that I don't care about. And it's order epsilon almost square. So I'm going to use my theorem again. I mean, I didn't say that my function f couldn't be a solution to another Poisson equation. So I'm going to call this part f and do it again. And that's the function k that you saw at the theorem at the beginning. So I do again my Poisson equation on the right-hand side. And then this pink term becomes a product of the moment generating function and the expectation of this function k. So then we put everything together and we're done. And before finishing, I'm almost done, let me recap. So we took a fairly complicated system, JSQ, where the parameters are Markov modulated. And we wanted to understand the distribution of the vector of Q lengths scaled by the heavy traffic parameter epsilon. The first step was state space collapse. So instead of analyzing this vector of Q lengths, we analyzed an equivalent single server queue. And the only condition we had is that lambda is large enough for each state I. Meaning that, for example, the Q could be unstable because that's a very large lambda, right? For some states I, and that's okay. And then in the second step, we deal with this single server queue. We use a transfer method. And when things get complicated, we estimate the covariance of the exponential function with the Markov-modulated terms using Poisson equation. And we obtain that beautiful theorem. All right, that's what I wanted to share today. I know I threw a lot at you, so happy to answer any questions.
All right, let's give Daniela a hand. Thanks, Daniela, for a great talk. So any questions?
Hi, Daniela. Thank you for a great talk.
Hi, Rhonda. It's good to see you.
Good to see you. Yeah, so I'm not, super familiar with the whole approach, but is it a reasonable intuition that somehow, is there a way we can think of covariances as capturing errors, right? That seems
Yeah.
like, can you give us an intuitive sense for why that's true?
Uh,
Aside from, all the math.
yeah. Yeah. So I call it an error because it's just the quantity I know how to deal with. Typically, so if we go back here, if I could compute the expectation of this and that um, separately, then I'm done.
Mm,
So, and I know I cannot do that. So instead, I'm going to see how this full expectation behaves,
uh-huh.
and the covariance just gives me what I want. So I don't actually have like a um, very concrete intuition besides just the math, honestly. Um,
Okay. Okay.
but
Well,
I mean, the only thing what I have in in my head, or what we had when we were doing it, is like I want the orange thing to be a parameter, right? I don't want it to be a function or a random variable, and the covariance happens to give me that.
okay. Okay. I yeah, so I wonder, I mean, the fact that it's not somehow more complicated,
Mm.
maybe, I mean, does that have something to do with it's a simple Markov chain or whatever? I mean, so maybe some of this comes out of like a Taylor series-ish thing. Why don't we need
Um,
any third moments or
So the fact that we get expectations and nothing more is because we're using transfer method. It's
yeah.
because we're dealing with moment generating functions. So instead of looking at distributions or higher moments, all I have is products of expectations.
Mm,
Um,
yeah. Okay.
uh,
Yeah. Okay.
yeah,
Okay.
and I mean another way to do this, and this is what Siva did in his paper for the switch, is instead of taking a one-step drift, he takes an m-step drift and then takes m to infinity, and then these two become independent because this part is mixed and this part is not.
Uh-huh.
So, but it's still the covariance. I mean, he still deals with the autocovariance function of the Markov chain.
Right. Right. Okay. Okay. Well, thank you. That's
Thank you.
Any other questions? Okay, Daniela, I have some questions.
Yes.
Okay, can you go back to uh, so when you so 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 basically you use V on you use several different Poisson equation solutions, right?
Oh, yeah.
So,
I think you want.
so I'm just curious, sort of, what are all the different quantities that you end up using?
So
So,
we basically want to decrease the order of the dependence of the
yeah,
moment-generating function and the Markov-modulated parameters. And in the first step, so we have
I see.
e to
So
the power q here and then some parameter here, and we decrease the order to an order epsilon term. So this one doesn't have an epsilon, so we pull out one epsilon, and then we still need to pull another one. So that's why we do another Markov modulate, another Poisson equation application here.
I see.
Does that make sense?
At least sort of. Uh,
And then I mean it's a very deep question, and with Easy we've been thinking about this particular thing, like why do we use it so many times? Or in particular, why do we use it in two parts? Um, and I don't have an answer besides decreasing the order of the multiplying term. And it's something that we see in other papers too. Like in particular, there's a paper by Fallin and then in 99, and they do a similar approach. They don't call it Poisson equation, but they do something similar and still need to do two applications of the two rounds of decreasing the order of the dependence. So there might be something fundamental that we don't quite understand there.
Interesting. Um, I'm also, yeah, I'm trying to connect this to, it's secretly the same thing. You can also sort of think of some of these as Palm expectations. It's not a necessarily very useful way to think about it because you
Uh-huh,
this
uh-huh.
that is like this would like whenever you're looking at the steady state product of something to do with your system state times the instantaneous arrival rate or the instantaneous
Mhm.
surface rate, right? You can rephrase that as a Palm expectation as sort of like expectation observed by arrivals or departures.
Right, right.
Not sure that's especially useful here. Um,
Honestly, I'm not super familiar with Palm calculus. It is something we looked at the beginning, and then we decided to go this route. I will have to think more about, or maybe we can
yeah,
discuss more about that approach because I don't think in Palm calculus, let's say it that way.
yeah. But this would sort of correspond, I think, to using the Palm inversion formula twice. So
Oh.
I'm trying to think if that means something. Anyway, okay, more pondering offline.
Well, I'm gonna make a note of that because that sounds great to even explore. I mean, we're working now on generalizing this to another system, so
Cool.
of course, understanding more will make it easier.
Yeah. Okay. All right. Well, I think with that, um, let's thank Daniela one more time. Um, and uh, and then and yeah, and so an announcement will be coming soon about the last Snap Talk of the semester, and then of course we'll see you again in the spring. All right. Bye.